Hello there. My name is Elara, and welcome to the Late Night Science Channel. Tonight, let me take you somewhere quiet, somewhere soft, a place where the world slows down and everything becomes simple again. We're going to drift into the gentle world of snow, not just as something cold or white, but as something almost magical, And if you find yourself enjoying this peaceful journey, I'd really appreciate it if you could hit that like button or subscribe. It helps these quiet science stories reach others who need them, and I promise it only takes a second. But for now, just let everything else fade away. Let your breathing slow and come with me into the hushed universe of falling snow. There's something about snow that changes everything it touches. The way it softens sharp edges, the way it hushes the world, the way it transforms an ordinary street into something from a dream. But what most people don't realize is that snow is so much more than frozen water falling from the sky. Each flake carries with it a story, a journey through clouds and cold air, a structure so intricate that no human hand could ever replicate it. And tonight, we're going to explore these stories together, slowly, gently, letting each fact settle like snowflakes on a winter evening. You see, when you look up at falling snow, you're witnessing something that began thousands of feet above your head. Up there in the cold darkness of the clouds, tiny particles float. Dust from deserts, salt from oceans, even microscopic fragments from space itself. These particles become the hearts of snowflakes, the seed around which everything else builds. A single water molecule drifts by, attracted to that particle, and freezes in place. Then another molecule joins it, and another, each one finding its position based on the temperature and the amount of moisture in the air at that exact moment. It's like watching a crystal cathedral build itself, one tiny brick at a time, following rules written into the very structure of water itself. The shape that forms depends on such delicate conditions. If the air is just a bit warmer, maybe around -2 degrees, the crystal grows into thin plates, flat hexagons that catch the light. But if it's colder, maybe -15 degrees, those same water molecules arrange themselves into columns instead, long, six-sided prisms that look like tiny pillars of glass. And in between these temperatures, in those narrow zones where the air hovers at just the right coldness, the crystals branch out into those classic star shapes we all recognize, with arms that reach outward in perfect symmetry. Each arm grows in the same way because each arm experiences the same conditions as it forms. But, and here's the beautiful part, no two snowflakes ever form in exactly the same place, tumbling through exactly the same path of air. So while the 6 arms of a single flake match each other, no two complete snowflakes in the history of Earth have ever been identical. Think about that for a moment. Every snowflake that has ever fallen from the beginning of winter itself has been unique. The one that landed on your glove when you were 7 years old, the one that melted on your cheek last January, the billions that are falling right now across mountains and forests and cities, each one different, each one a tiny frozen sculpture that exists for just a brief moment before it changes into something else. There's something deeply peaceful about that, isn't there? This endless creativity happening in silence, with no audience, no purpose, except to exist and then dissolve back into the world. As snowflakes drift downward, they don't fall in a straight line like you might think. They flutter, they swirl, they dance through currents of air that we can't see. A flake might rise briefly on a warm updraft, hover for a second, then spiral down through colder air. This wandering path means each flake has time to grow, collecting more water vapor as it travels, building its structure outward layer by microscopic layer. Some flakes collide with others and stick together, forming those big puffy clusters that fall faster and land with a soft plop. Others remain separate, staying light and dry, floating so slowly that a gentle breath of wind can carry them sideways for meters before they finally settle. The journey from cloud to ground might take 20 minutes, maybe an hour for the smallest crystals. During all that time, the flake is constantly changing. If it passes through a pocket of warmer air, some of its edges might melt slightly, then refreeze when it enters cold air again. If it tumbles through an area with lots of moisture, new layers build up quickly. If the air is dry, the flake might actually shrink a bit, losing some of its water to sublimation, that strange process where ice turns directly into vapor without melting first. By the time the flake reaches the ground, it carries within its structure a complete record of its journey, a frozen diary of every temperature zone it passed through, every humidity level it encountered. When snow finally lands and begins to accumulate, something remarkable starts to happen beneath the surface. Those individual crystals, with each its own shape, begin to change. The points and branches that looked so delicate start to round off as water molecules migrate from sharp edges to flatter surfaces. This happens because nature always moves toward the most stable arrangement, and sharp points are unstable. They hold too much energy in a small space. So slowly, over hours and days, the snow transforms from a layer of distinct crystals into a mass of rounded grains, all pressed together but not quite touching, with air spaces between them. These air spaces are what makes snow such an incredible insulator. Air doesn't conduct heat very well, and when you trap lots of tiny air pockets inside a material, you create something that barely lets warmth pass through at all. A thick layer of snow can keep the ground beneath it hovering right around the freezing point, even when the air above is bitterly cold, -20 or -30 degrees. Plants and small animals take advantage of this. Seeds wait dormant in soil beneath the snow, protected from the worst of winter. Mice and voles create entire tunnel systems in the space between the snow and the ground, a hidden world called the sub-Nevian zone, where temperatures stay relatively mild and predators can't reach. The way snow reflects light is something that artists and photographers have tried to capture for centuries, never quite succeeding. Fresh snow can reflect up to 90% of the sunlight that hits it, which is why snow-covered landscapes are so bright they can almost hurt to look at. This happens because each snow grain acts like a tiny mirror with countless surfaces, and light bounces from grain to grain, scattering in every direction. Blue light scatters a bit more than red light, which is why shadows on snow often look pale blue rather than gray. And deep inside a thick snowpack, where sunlight has scattered through hundreds of layers, the color becomes this intense, otherworldly blue, the kind of blue you see inside glacial crevasses or beneath overhanging cornices. But snow doesn't just reflect visible light. It also reflects heat in the form of infrared radiation, and this has a powerful cooling effect. On a clear night after fresh snow has fallen, the temperature can drop dramatically because the snow is radiating heat back into space, and the clear sky has nothing to reflect it back down. This radiative cooling can make a snowy night feel much colder than a cloudy night at the same temperature. The snow itself also cools the air right above it through direct contact, creating a thin layer of extra cold air that clings to the surface. Walk across a snowy field at night, and you can sometimes feel this cold layer around your ankles, distinctly chillier than the air at chest height. As winter progresses and more snow accumulates, the older layers beneath get compressed by the weight above them. This compression squeezes out some of the air and brings the grains into closer contact. Over time, the deeper snow becomes denser and harder, not quite ice, but not quite snow either, something in between that mountaineers call firn. In places where snow never fully melts, like high mountains or polar regions, this process continues year after year. The fern gets buried under new snow, compressed further, and eventually, after decades or centuries, it transforms into glacial ice, so dense and blue and ancient that it holds bubbles of air from atmospheres long gone, preserves pollen from forests that have vanished, records volcanic eruptions that no human witnessed. There's a sound that snow makes, or rather a collection of sounds that only exist in winter. When you walk on fresh, cold snow, it squeaks under your boots. This happens because you're crushing countless tiny ice crystals, and each one breaks with a faint crack. When the temperature is far below freezing, maybe -15 or colder, the snow is dry and rigid enough that all those little cracks happen at once, creating that characteristic squeak. But when the temperature rises, even just a few degrees, the snow becomes softer, the crystals can compress without breaking, and the squeak disappears, replaced by a softer crunch. You can actually estimate the temperature just by listening to the sound your footsteps make. Falling snow makes its own sound too, though it's so quiet most people never notice it. In perfectly still air, when large flakes are falling heavily, there's a faint hissing rustle, like the whisper of tissue paper. It comes from the flakes brushing against each other and against the surface of whatever they're landing on. It's easiest to hear in a forest, where the trees block wind and the snow falls straight down through the branches. Stand perfectly still and listen, really listen, and you might catch it, that soft, continuous shush that seems to come from everywhere and nowhere at once. Some people find it unsettling, but most find it deeply peaceful, a sound that seems to slow time itself. Snow also changes other sounds, absorbing them in ways that make winter landscapes feel muffled and distant. The open structure of snow, all those air pockets between grains, traps sound waves and prevents them from bouncing back. This is why everything seems quieter after a heavy snowfall. Voices don't carry as far, traffic noise fades more quickly, even bird calls sound softer and closer, as if the world has been wrapped in a blanket that soaks up noise before it can travel. On the other hand, hard-packed snow or ice can reflect sound beautifully, which is why you can sometimes hear conversations or footsteps from surprisingly far away across a frozen lake. The temperature at which snow melts is something we think we know, but it's actually more complicated than just saying 32 degrees. Pure ice does melt at that temperature, but snow isn't pure. It contains dust, pollen, dissolved gases, sometimes salt if it's near roads. All these impurities lower the melting point slightly. Plus, when sunlight hits snow, it doesn't just warm it from the outside. Some light penetrates into the snow, getting absorbed by any darker particles buried inside, and these particles heat up, creating little melt zones deep in the snowpack, even when the surface is still frozen solid. You can sometimes see this effect when dark stones or bits of bark sink down into the snow, carving vertical holes around them as they melt their way through. Another factor is pressure. When you press on snow, you increase the pressure at that point, and higher pressure lowers the melting point of ice. This is part of why skis and sleds glide. They create a thin film of liquid water beneath them through pressure and friction, and that water acts as a lubricant. It's also why snow is easier to pack into snowballs when the temperature is near freezing. There's a bit of melt at every contact point, and when you release the pressure, that melt refreezes, gluing the crystals together. In very cold weather, snow won't pack at all because you can't generate enough pressure to create that crucial bit of melt. When snow does begin to melt in spring, it doesn't disappear evenly. South-facing slopes get more sun and melt first. Areas beneath trees melt slower because the canopy blocks sunlight. Snow around tree trunks melts faster because the dark bark absorbs heat and radiates it outward. The result is a matchy landscape where snow persists in some spots while bare ground appears in others, creating a mosaic that changes day by day.
This uneven melting has ecological importance because it means not all plants start growing at once. It staggers the seasons, giving different species their moment, spreading resources over time. Meltwater itself behaves in interesting ways. Because it's cold, very close to freezing, it's denser than warmer water and tends to sink when it enters streams or lakes. This can create layers, with cold meltwater flowing along the bottom while warmer water sits on top. The chemistry of meltwater is unique too. Snow accumulates whatever falls from the sky: dust, pollen, dissolved gases, and all of this gets released when the snow melts. The first pulse of meltwater in spring is often quite dirty, carrying away a winter's worth of atmospheric deposition all at once. This initial flush can temporarily change the chemistry of streams and ponds, affecting the organisms living there. In mountains, melting snow is the source of most rivers. High peaks hold vast amounts of frozen water that melts slowly throughout late spring and summer, feeding streams long after the rain has stopped. Communities far from the mountains depend on this steady flow, using snowmelt for drinking water, irrigation, hydroelectric power. The amount of snow that accumulates each winter determines how much water will be available months later, which is why scientists spend so much time measuring snowpack, skiing, or flying into remote areas to stick probes into the snow and calculate its water content.
Avalanches are part of snow's story too, though they're the dramatic, dangerous side of something that's usually gentle. An avalanche happens when a layer of snow loses its grip on the slope beneath it and begins to slide. This can occur when new snow piles up faster than the old snow can adjust, or when a weak layer deep in the snowpack collapses, or when temperatures rise and melt begins to lubricate the layers. Once it starts, an avalanche can accelerate to highway speeds, carrying thousands of tons of snow down the mountain, snapping trees, burying everything in its path. The snow in an avalanche isn't fluffy anymore. The violence churns it into a dense, heavy mass that sets like concrete when it stops, making rescue extremely difficult. But even this destructive force plays a role in mountain ecosystems. Avalanche paths clear narrow strips of forest, creating meadows where different plants can grow, where elk and deer come to graze, where birds find open hunting grounds. The snow from avalanches can dam streams temporarily, creating ponds that last through summer. And the huge amount of snow deposited at the bottom of the path melts slowly, keeping that area cool and wet long after surrounding areas have dried out. Nothing in nature is purely destructive. Even avalanches reshape the landscape in ways that some species depend on. Snow also has a relationship with wind that creates structures you might have seen without knowing what they are. When wind blows across open snow, it picks up loose crystals and carries them along, similar to how wind moves sand in a desert. When the wind slows or hits an obstacle, it drops the snow, building up drifts. These drifts form on the downwind side of obstacles, creating smooth, curved shapes that look sculpted. Cornices are dramatic examples, overhanging shelves of snow that build out from ridges, growing as wind-driven snow piles up and then curls over the edge. They can extend several meters into empty air, supported only by the interlocking crystals that have been deposited grain by grain. Sastrugi are smaller features, wind-carved ridges and grooves that form in snowfields. They look like frozen waves, all aligned with the prevailing wind. In polar regions where wind is constant and fierce, sastrugi can make the surface almost impossible to walk across, a chaotic jumble of knee-high ridges running in every direction. The shapes evolve as wind direction changes, old ridges eroding while new ones form, the whole landscape shifting slowly like something alive. There is also something called snow rollers, which are exactly what they sound like. When conditions are perfect, a bit of snow can break loose on a slope and start rolling downhill, collecting more snow as it goes, growing into a cylinder. Because the core is often loose and the outer layers are denser,
the middle can collapse, leaving a hollow roll that looks like a snow donut. These form rarely because you need sticky snow, a good slope, and just the right amount of wind. But when they do appear, they're scattered across hillsides like someone has been playing with snow sculptures. Snow crystals themselves continue to fascinate scientists because the physics that creates them is still not completely understood. The hexagonal shape comes from how water molecules bond together. They naturally form six-sided structures at the molecular level. But why a particular temperature produces plates while another produces columns? Why some crystals grow elaborate branches while others stay simple? These questions involve complex interactions between temperature, supersaturation, crystal growth rates, and probably factors we haven't even identified yet. Every winter, researchers still make new observations, finding crystal types they've never documented before. One particularly strange form is called triangular snow crystals, rare formations that have threefold symmetry instead of sixfold. They occur under very specific atmospheric conditions and are so unusual that most people have never seen one. There are also hollow columns, capped columns, split plates and stars, columns with plates at the ends, combinations that seem to violate the rules but appear nonetheless. Each one formed somewhere in the clouds, under a unique set of conditions, for reasons we're still piecing together. The size of snowflakes varies wildly. Most are a few millimeters across, but in warm, wet conditions, they can grow much larger. The largest snowflake ever reported was supposedly 15 inches across, observed in Montana in 1887. Whether that measurement was accurate is debated, but there are verified reports of snowflakes 4 or 5 inches wide, massive clusters of hundreds of individual crystals all stuck together. These giants fall in climates where snow is rare, places where the air near the ground is barely below freezing, allowing the wet, sticky flakes to collide and merge on their way down. At the other extreme are diamond dust crystals, tiny plates or columns that form in clear, extremely cold air. These are so small they barely fall, drifting on the slightest breeze, catching sunlight and glittering. In polar regions, diamond dust can create halos and light pillars around the sun, optical displays where the crystals act like millions of tiny prisms, bending light into rings and arcs. Walking through diamond dust feels like moving through a cloud of stars, each crystal a pinpoint of reflected light that vanishes when you try to focus on it. Snow and ice also host their own ecosystems, believe it or not. Certain algae can live on the surface of snow, tinting it pink or green or even red. These snow algae have adapted to survive freezing temperatures and intense ultraviolet radiation from sunlight bouncing off the white surface. They grow slowly throughout winter, then bloom in spring, sometimes covering entire snowfields with Elara. When animals eat the algae, they ingest the pigments, which can tint their own bodies. Bears in some regions have pinkish fur from eating salmon that ate algae that grew on snow, a connection that links the food chain back to these hardy microorganisms. Ice worms are another strange adaptation, tiny segmented worms that live in glacial ice, feeding on algae and pollen that gets trapped in the surface. They're most active when temperatures are right around freezing. They actually die if they get too warm, even just a few degrees above zero. These worms spend their entire lives in ice, wriggling through the microscopic spaces between crystals. And if the glacier melts, they melt with it, unable to survive in the world beyond their frozen home. There are also ice spiders, springtails, and other tiny arthropods that live on glaciers, creating food webs in places that seem too harsh for life. These creatures feed on wind-blown pollen, seeds, and dead insects, thriving in temperatures that would kill most species. They represent life's incredible persistence, its ability to find a foothold in even the most extreme environments. The relationship between snow and climate is complex and self-reinforcing. More snow means more sunlight gets reflected back to space, which cools the planet, which can lead to more snow. But as the planet warms, snow melts earlier, exposing darker ground that absorbs sunlight, which warms the planet further, which melts more snow. This feedback loop works in both directions, and is one reason why Earth's climate can shift between ice ages and warm periods. Small changes get amplified through these reflective effects until the whole system flips into a new state.
Right now, we're seeing snow patterns change, arriving later in autumn, melting earlier in spring, accumulating less in some regions. These shifts affect water supplies for billions of people, change the timing of plant growth, alter animal migration patterns, influence weather systems. Snow isn't just a pretty feature of winter, it's a critical component of how Earth's climate functions, and watching it change gives us real-time evidence of larger transformations happening across the planet. In culture, snow has always held a special place. It's associated with purity, renewal, silence, death, beauty, danger. Different languages have multiple words for different kinds of snow because the distinctions matter when your life depends on understanding the frozen landscape. In some traditions, the first snowfall of the year is celebrated as a moment of transition, the earth closing its eyes for winter's sleep. In others, snow is seen as a blessing, bringing water that will nourish crops when it melts. The science of snow is called nivology, from the Latin word for snow, and it's a field that combines physics, chemistry, meteorology, hydrology, and ecology. Nivologists study everything from how individual crystals form to how continent-sized ice sheets flow. They work in laboratories growing crystals under controlled conditions, and they work in the field, digging snow pits in remote mountains, measuring layers, testing strength, trying to predict avalanches, or understand how snowpack will melt. Some of the tools they use are remarkably simple, like a magnifying glass and a black background to examine crystal types, or a probe to measure snow depth. Others are sophisticated, like ground-penetrating radar to map layers deep in a glacier, or satellites that measure how much sunlight snow reflects across entire regions. But regardless of the tools, the goal is the same: to understand snow in all its complexity, to see beyond the white blanket and grasp the intricate processes underneath. There's a particular kind of snow that forms on cold objects when fog rolls in, called rime ice. It's different from frost, which forms when water vapor freezes directly onto a surface. Rime forms when supercooled water droplets in fog hit an object and freeze instantly on contact. The result is a coating of ice that builds up into elaborate feathery structures, always growing into the wind, because that's the direction the fog is coming from. Trees coated in thick rime ice look like they're made of white lace, every branch outlined in delicate frozen fronds. These formations can become so heavy they break branches, especially if the wind is strong enough to keep the fog coming for hours. Another phenomenon worth mentioning is frost flowers, not to be confused with actual flowers, but strange ice formations that grow on new sea ice. When the ocean freezes in calm conditions, the thin ice acts as a barrier, but salt-rich water beneath it can wick upward through tiny cracks. When this salty water hits the cold air, it freezes into delicate flower-like structures made of ice crystals. These frost flowers are incredibly salty and are important for atmospheric chemistry because when they form, they release bromine and other chemicals into the air, which can affect ozone levels in polar regions. The connection between snow and ecosystems extends beyond just plants and animals. Snow affects soil microbes, those invisible organisms that break down dead material and recycle nutrients. Under snow, microbial activity continues slowly, and the microbes produce carbon dioxide and other gases that get trapped beneath the snowpack. When spring comes and snow melts, these gases are released in a pulse, temporarily increasing the carbon dioxide concentration at ground level. In forests that experience long winters, this spring pulse is a significant part of the annual carbon cycle. Snow also provides habitat in unexpected ways. Certain insects lay their eggs in leaf litter in autumn, and the larvae develop slowly through winter beneath the snow, protected from the worst cold. Snowflakes, which aren't actually fleas, but a type of springtail, emerge on warm winter days and gather on snow surfaces, looking like pepper scattered across the white. They're active when temperatures are just above freezing, feeding on decaying plant material and microbes. When it gets colder, they disappear back into the protection of the snowpack. The speed at which snow accumulates can vary dramatically over short distances, from a gentle dusting over hours to a rapid burial in minutes during intense storms. In lake effect snow events, cold air moving over warm water picks up enormous amounts of moisture, which then falls as snow when the air hits land. These can produce snowfall rates of several inches per hour, piling up several feet in a single day. Communities near large lakes plan for these events, knowing that one storm can shut down roads and schools, bury cars, turn familiar streets into deep canyons of white. Mountain snow behaves differently from flatland snow because of elevation and terrain. As air rises up a mountainside, it cools, and cooling air drops its moisture. This is why mountain ranges often have heavy snow on the windward side and dry conditions on the leeward side. The Cascades in Washington, the Sierra Nevada in California, the Alps in Europe, all these ranges create their own snow climates, wringing moisture out of passing storms and piling it in high alpine basins where it can sit for months or even years before melting. At night, especially clear nights, snow on the ground can glow faintly. This isn't bioluminescence, it's just the reflection of starlight and moonlight from billions of ice crystals, each one catching a photon and bouncing it back toward your eyes. Walking in a snowy landscape under a full moon creates this strange twilight effect, where you can see fairly well despite the hour, the snow acting like a natural light amplifier. Some people report that this reflected light has a blue tint, colder and more ghostly than sunlight, though whether this is an optical effect or something our brains add isn't entirely clear. Snow depth can vary dramatically over short distances because of wind and terrain. In open fields, wind scours snow from high spots and deposits it in low spots, creating bare patches next to deep drifts. Around buildings, snow fills in corners and piles against walls, especially on the side opposite the prevailing wind. In forests, snow depth depends on the canopy. Dense evergreen forests intercept snow in their branches, and some of it sublimates before reaching the ground, so the snowpack beneath old growth might be thinner than in a nearby clearing. These variations in snow depth matter for animals trying to move around. Deep, soft snow is exhausting to travel through. Each step requires lifting your foot high and breaking through the crust. This is why deer often follow the same trails all winter, packing down the snow so they can move more efficiently. Predators use these trails too, knowing prey will eventually use them. Some animals have evolved wide feet, snowshoe hares for instance, that distribute their weight and let them stay on top of snow that would swallow other creatures. The weight of snow is something people often underestimate. Fresh, fluffy snow might only weigh a few pounds per cubic foot, but settled snow can weigh 20 pounds per cubic foot, and wet, compact snow can exceed 30 pounds. When you calculate how much snow sits on a roof, the weight adds up quickly. A square foot of roof covered with 2 feet of heavy snow is supporting 60 pounds.
Multiply that by the area of the roof, and you're talking about tons of weight pressing down on the structure. This is why building codes in snowy regions require strong roofs, and why people shovel roofs when the snow gets too deep.
Glaciers, those massive rivers of ice, are essentially snow that never melted, accumulated over centuries, compressed into ice, and set in slow motion by gravity. A glacier forms in a place where more snow falls in winter than melts in summer, so year after year the snow builds up. The weight of new snow compresses the old snow beneath it, squeezing out air, fusing grains together, eventually creating solid ice. When the ice gets thick enough, usually at least 100 feet or so, it begins to flow, deforming under its own weight, sliding over the bedrock, carving valleys, plucking rocks, grinding stone into flour. Glaciers move slowly, often just inches per day, but they're immensely powerful. The ice at the bottom is under so much pressure that it can melt even when the surface temperature is far below freezing, creating a film of water that lubricates the base. Rocks embedded in the bottom of the glacier act like sandpaper, scraping grooves into bedrock that can still be seen thousands of years after the ice has melted. Glaciers also contain enormous amounts of rock debris, carrying it for miles before depositing it in piles called moraines. The blue color of old glacial ice comes from the same physics that makes the sky blue, except in reverse. Red light penetrates deep into the ice and gets absorbed, while blue light scatters back toward your eyes. But this only works with very dense ice that has lost almost all its air bubbles. The deeper you go into a glacier, the older and denser the ice, the more intense the blue. Inside ice caves or crevasses, the blue can be so pure and vivid, it looks almost artificial. Glaciers also contain bubbles of ancient air, trapped when snow compressed into ice. Scientists drill cores from glaciers and ice sheets, extracting cylinders of ice that extend back thousands of years. By analyzing the air in those bubbles, they can measure the composition of Earth's atmosphere in the past, how much carbon dioxide was present, what the temperature was, whether there were volcanic eruptions or forest fires. Ice cores are like climate time machines, preserving a detailed record that no other archive can match. One of the strangest things about old ice is that it can contain living organisms. Bacteria and other microbes get trapped in the ice and enter a dormant state where they're not really alive, but not quite dead either. When the ice melts or scientists bring a core back to the lab and thaw it carefully, some of these microbes wake up after thousands or even hundreds of thousands of years. They've survived longer than any species of large animal, waiting in the frozen dark, and when conditions return to something they can tolerate, they resume metabolic activity, as if no time has passed at all. Snow and ice also play a role in mountain weather by creating their own local climates. A large snowfield or glacier cools the air above it, creating a zone of cold, dense air that can flow downhill like water, especially at night. These katabatic winds can be strong and persistent, shaping where plants grow, how storms develop, even where people choose to build settlements. On a smaller scale, the cold air around snow can create temperature inversions, where valleys are colder than hilltops, trapping fog and pollution in low areas, while hilltops bask in clear sun. The transition from snow to bare ground in spring, often called snowmelt season, is a critical time for ecosystems. As snow melts, it releases water gradually, keeping streams full and the ground moist. But it also releases nutrients that accumulated in the snow over winter, nitrates and other compounds that plants need. This pulse of nutrients, combined with increasing sunlight and warmth, triggers a rapid green-up. Plants that were dormant suddenly begin to grow, racing to capture resources before the ground dries out in summer. For some plants, the timing of snowmelt determines their entire strategy. Early snowmelt species are adapted to start growing as soon as snow disappears, taking advantage of moist soil before other plants can compete. Late snowmelt species, often found in shaded spots or high elevations where snow persists, wait longer but then grow rapidly in the short window they have. The date when snow disappears from a particular spot can vary by weeks from year to year, and plants have to be flexible enough to handle that variability. Animals time their reproduction around snowmelt too. Many birds arrive on breeding grounds just as snow is retreating, when insects are emerging and fresh vegetation is appearing. Arrive too early and there's nothing to eat. Arrive too late and the best nesting sites are taken. This creates selection pressure for accurate timing, and many species use day length or weather cues to predict when conditions will be right hundreds of miles away at their destination. Snow avalanches, despite being destructive, actually create unique habitats over time. Avalanche paths are long strips down mountainsides where snow slides repeatedly, preventing trees from growing. Instead, these paths fill with shrubs, grasses, and flowers that can regrow quickly after being knocked down. Moose and elk feed heavily in avalanche paths because the vegetation is nutritious and easy to reach. In winter, the paths can be useful corridors for animals trying to move through deep snow, since the avalanche often compacts or removes the snow entirely. The sound of an avalanche is something people who've experienced one never forget. It starts as a deep rumble, almost subsonic, felt more than heard. Then comes a roar like a freight train or a waterfall, growing louder and louder as thousands of tons of snow accelerate down the slope. The moving snow creates a pressure wave and can knock down trees and damage buildings even before the snow itself arrives. And then, often as quickly as it started, silence. The avalanche has passed, leaving behind a new landscape buried under meters of debris. Predicting avalanches is part science, part art. Forecasters look at snowpack structure, weather patterns, recent wind and temperature changes, the slope angle and shape. They dig pits to examine the layers, looking for weak layers buried under stronger ones. They perform tests, cutting blocks of snow and seeing if they slide, measuring how much force it takes to trigger a failure. But even with all this information, avalanches can still surprise, triggered by factors that weren't obvious, by a combination of conditions that hadn't occurred before. In some ways, snow is the most temporary features of Earth. It arrives, transforms the world, and then disappears, leaving almost no trace. Unlike mountains or rivers or forests, which persist for millennia, snow belongs to the season, existing only as long as conditions allow. Yet in that brief time, it exerts enormous influence, shaping water cycles, supporting ecosystems, affecting human societies. It's both fragile and powerful, soft and yet heavy enough to crush buildings, beautiful and potentially deadly. The experience of snow is deeply personal and varies by culture. For people who live with snow every year, it's a familiar companion, sometimes welcome, sometimes a nuisance, but always expected. For people in warm climates who rarely see snow, it's a novelty, something magical that appears briefly and then vanishes. Children everywhere seem to share the same joy when snow falls, the excitement of a transformed world, the opportunities for play, the sense that normal rules have been suspended. And there's something meditative about snow, the way it simplifies the world visually. Colors disappear under white, shapes become smoother, details are erased. A complex, busy landscape becomes clean and quiet. Falling snow adds to this by obscuring the distance, creating a soft white curtain beyond which nothing is visible. In heavy snow, the world shrinks to just a few meters around you, and there's a strange comfort in that, a sense of being in a small, safe bubble, even as the storm rages.
Walking in fresh snow is an experience everyone should have at least once. That moment when you step into untouched snow and your foot sinks down, the slight resistance and then the give, the perfect imprint left behind. The way snow clings to your boots and your clothes, melting where it touches skin, staying frozen where it touches fabric. The silence, except for your own breathing and footsteps, the sense that you're the only person in the world at that moment. Looking at snow through a microscope or even just a strong magnifying glass is revelatory. Those perfect geometric shapes, the delicate branching patterns, the fact that these structures assemble themselves automatically from nothing but water vapor and cold air, it's almost unbelievable. Each crystal is a tiny work of art created by physics, existing for minutes or hours before it merges with other crystals or melts away. And during a single snowstorm, trillions upon trillions of these crystals fall, each one unique, each one following the same laws, but arriving at a different result. Snow has this ability to make familiar places look completely foreign. A street you walk every day becomes unrecognizable under deep snow. Landmarks disappear, distances seem different. This transformation is part of why snow feels magical. It's a reminder that the world we think we know is actually quite changeable, that nature can redraw everything overnight. And when the snow melts, the world returns, but somehow it looks a little different, as if the snow left behind some trace of its presence even after vanishing. The relationship between temperature and snow type creates an entire vocabulary that people who live with snow understand intuitively. There's powder, that dry, light snow that falls when temperatures are well below freezing, the kind skiers dream about because it doesn't pack down, it just floats. Then there's wet snow, heavy and sticky, perfect for snowballs and snowmen, falling when temperatures hover right around freezing. Corn snow forms in spring, when repeated melting and freezing creates rounded grains that look like tiny ball bearings. Crud is chopped up snow that's been skied or walked on until it's an uneven mess. And névé is old snow that's been through multiple melt-free cycles and compressed into something between snow and ice. Each of these types behaves differently. Powder flows like liquid. You can almost swim through it, while wet snow clumps and sticks to everything. Corn snow is fast and fun to ski on, but can be treacherous if it's not fully frozen. Understanding these distinctions isn't just for recreation. It matters for safety, for predicting how snow will behave, for knowing when slopes are dangerous or trails are passable. In the high Arctic and Antarctic, snow behaves in ways that seem alien compared to what most people experience. Temperatures can be so cold that snow doesn't behave like we expect at all. It becomes more like sand, individual grains that barely stick together, shifting and flowing in the wind. The crystals are often tiny, formed in such cold air that they can't grow large. And because the air is so dry, sublimation happens constantly, snow evaporating directly into vapor without melting, so the landscape is slowly losing snow to the atmosphere even when it never gets warm. Diamond dust, which I mentioned earlier, is common in these polar regions, filling the air on clear, cold days. These tiny crystals create optical phenomena that are almost otherworldly. Sundogs, those bright spots on either side of the sun, form when diamond dust crystals align horizontally and refract sunlight at precise angles. Light pillars appear when crystals are aligned differently, creating vertical beams that extend above and below the sun or moon. And on rare occasions, all these effects combine into complex displays with multiple rings, arcs, and pillars filling the sky, turning the atmosphere into a giant kaleidoscope. The way snow interacts with wind creates patterns on the surface that tell stories about recent weather. Wind ripples, looking like frozen waves, form when moderate wind moves loose snow. Zastrigi, those sharp ridges I mentioned before, indicate stronger, more persistent wind. Smooth patches mean the area was sheltered, while scoured patches mean wind was funneling through at high speed. Reading these signs is crucial for travelers in snowy regions. They indicate where drifts might be deep, where hidden obstacles might lurk, where the safest route lies. Snow fences, those wooden or plastic barriers you see along highways and snowy areas, work by manipulating how snow deposits snow. The fence creates turbulence on its downwind side, causing the wind to slow down and drop its load of snow. This creates a drift behind the fence instead of on the road, keeping the pavement clear. It's a simple but effective technology that's been used for over a century. The optimal fence design, spacing, and height have all been studied extensively because even small improvements can save significant time and money in snow removal. In some cultures, snow is harvested and stored for use through summer. Traditional snow houses in Japan collected snow in insulated buildings where it would last for months, providing refrigeration before electricity. This practice is seeing a revival in some places as an energy-efficient cooling method. The snow slowly melts, but the cold it produces can be used to cool buildings or preserve food, essentially storing winter's cold for summer's heat. Snow also plays a role in hydrology beyond just being a source of meltwater. The timing of snowmelt affects stream temperatures, which affects what fish species can live there. Cold meltwater entering streams in spring and early summer keeps them cool enough for trout and salmon, species that need cold water to survive. If snow melts earlier or faster because of warming temperatures, streams warm up sooner, potentially making them inhospitable for cold water species. This is one of the more subtle but important ways that changing snow patterns affect ecosystems. The structure of a snowpack can be incredibly complex, with dozens of distinct layers formed by different storms and weather conditions. Each layer has its own grain size, density, temperature, and mechanical strength. How these layers bond to each other determines how stable the snowpack is. Strong bonds mean the snow will stay in place on steep slopes. Weak bonds mean it might slide. Avalanche forecasters spend hours examining these layers, documenting their properties, testing how they interact, trying to predict what will happen when you add new snow or when temperatures change. There are weak layer types that avalanche experts watch for especially carefully. Surface hoar forms on clear, cold nights when water vapor freezes directly on the snow surface, creating large, delicate crystals that look like frost feathers. These crystals are beautiful but structurally weak, and when they get buried under new snow, they create a slippery layer that the upper snow can slide on. Depth hoar forms near the ground when there's a strong temperature gradient in the snowpack, creating large, angular crystals with very little strength. And faceted snow, with its geometric shapes, also forms under temperature gradients and can persist for weeks or months as a weak layer waiting to fail. The instruments used to study snow range from simple to sophisticated. A snow pit is just a hole dug into the snowpack, but it reveals everything about how the snow has accumulated and changed. A crystal card is a black piece of velvet or plastic that makes white snowflakes easy to see and photograph. A penetrometer measures how much force it takes to push a probe through snow, indicating its hardness. And at the high-tech end, ground-penetrating radar can see the layering inside a snowpack without digging, while weather stations on remote peaks automatically record temperature, wind, and snow depth, transmitting data via satellite.
Snow science has applications beyond avalanche forecasting and water management. Understanding how snow reflects sunlight helps climate scientists model Earth's energy balance. Studying how snow conducts heat informs building design in cold climates. Research on ice crystal formation helps meteorologists improve weather forecasts. And investigations into how snow supports ecosystems inform conservation planning. Snow touches so many aspects of Earth's systems that studying it means studying a bit of everything. There's also an aesthetic dimension to snow science, a recognition that these processes produce beauty as a side effect of physics. The branching patterns of dendrites follow mathematical rules, but create infinite variation. The blue of glacial ice is precise science, but also pure visual wonder. The silence of falling snow is acoustic physics, but also a profound experience. Scientists who work with snow often talk about this duality, how understanding the mechanisms doesn't diminish the beauty, it enhances it, adding layers of meaning to what you're seeing. Hoarfrost, which is different from rime ice, forms on cold surfaces when water vapor in the air freezes directly without becoming liquid first. It creates delicate, feathery structures that look like someone painted the world with white lace.
Hoarfrost is most dramatic on plants, where it outlines every stem and leaf with crystalline detail. It forms on cold, clear nights when humidity is relatively high, and it can grow surprisingly thick, building up over hours into structures that seem too delicate to exist. By mid-morning, as sunlight warms things up, hoarfrost sublimates away, disappearing directly from solid to gas, leaving no trace of its brief existence. The formation of lake ice is a process worth understanding because it's more complex than just water freezing. As a lake cools in autumn, the surface water gets denser and sinks, mixing with deeper water. This continues until the entire lake reaches about 4 degrees Celsius, the temperature at which water is densest. Below that temperature, water becomes less dense as it cools, so the coldest water stays at the surface. When the surface finally reaches 0 degrees, ice begins to form. This ice floats because it's less dense than water, and it forms a layer that insulates the water below, slowing further freezing. This is why lakes freeze from the surface down rather than from the bottom up, and why deep lakes might never freeze completely. The ice on a lake is dynamic, constantly responding to temperature changes. It expands when it cools and contracts when it warms, creating stress that releases as cracks and booms. These sounds can be startling if you're not expecting them, deep, resonant groans that seem to come from everywhere at once. The ice is also flexible, bending under weight rather than immediately breaking, which is why it can sometimes support heavy loads even when it seems thin. But this flexibility has limits, and judging when ice is safe requires experience and caution. Black ice on lakes is especially beautiful, clear enough to see straight through to the water below. It forms when the lake freezes quickly under calm conditions, creating ice with few bubbles or imperfections. Looking down through black ice feels surreal, like walking on invisible glass suspended over water. You can see rocks on the bottom, fish swimming, aquatic plants swaying. It's disorienting in a wonderful way, breaking your sense of what's solid and what's not. In contrast, white ice is opaque because it contains countless tiny air bubbles. This forms when snow falls on ice and then melts and refreezes, or when ice forms slowly with lots of dissolved air in the water. White ice is weaker than black ice of the same thickness because those air bubbles are points of weakness where cracks can propagate. This is why experienced ice travelers prefer black ice and avoid white ice when they have a choice. Pressure ridges form on large lakes and sea ice when the ice sheet cracks and then is pushed together by wind or currents. The edges buckle upward, creating ridges that can be several meters tall, chaotic jumbles of broken ice. These ridges are barriers to travel, and also places where the ice is under significant stress. They're also beautiful in their own way, sculptural formations that catch light and shadow, that groan and shift as the ice continues to move. When sea ice forms, it's different from lake ice because of the salt. As the ocean surface freezes, most of the salt is excluded from the ice crystal structure, but some remains trapped in tiny pockets of brine. These brine channels I mentioned earlier are a network of liquid veins running through the ice, and they're warmer and saltier than both the ice and the seawater below. Over time, as the ice gets colder, some of this brine drains out, making the ice less salty and stronger. But those channels remain as weaknesses in the structure, affecting how the ice breaks and how it transmits light and sound. Sea ice also supports a unique ecosystem different from lake ice. Algae grow on the undersurface of the ice where sunlight can still penetrate, forming a greenish-brown layer. Small crustaceans graze on this algae, and fish feed on the crustaceans, creating a food web that exists in the boundary between ice and water. For polar bears, seals, penguins, and countless other species, sea ice is habitat, hunting ground, and highway all at once. Changes in sea ice extent and duration have cascading effects through entire ecosystems. The seasonal advance and retreat of sea ice is one of the most dramatic rhythms on Earth. In the Arctic, sea ice reaches its minimum extent in September, after summer melting, and its maximum in March, after winter growth. The difference is millions of square kilometers, an area larger than the continental United States appearing and disappearing every year. Satellite images show this pulse clearly, the white ice advancing from the pole each autumn, retreating each summer, a breathing motion that's continued for as long as there have been polar regions. But this rhythm is changing. Sea ice is forming later, melting earlier, and the minimum extent is shrinking. This has enormous implications for climate, because ice reflects sunlight while open water absorbs it. So less ice means more warming, which means less ice, a feedback loop that's difficult to reverse. It also affects everyone who depends on sea ice, both humans and wildlife, forcing adaptations to a rapidly changing environment. Ice roads and ice bridges are temporary infrastructure created by freezing temperatures. In regions where water bodies separate communities, a thick layer of ice can become a highway for part of the year, supporting cars, trucks, even heavy equipment. Building an ice road requires careful monitoring of ice thickness and temperature, flooding the surface to build up layers, maintaining the route throughout winter. When spring comes, these roads disappear, and travel has to revert to boats or long detours. Some communities are finding their ice road seasons getting shorter, which has real economic and social impacts.
Glacial ice caves form when meltwater carves tunnels through or beneath glaciers. These caves are temporary and dangerous, constantly changing as the ice melts and moves. But they're also spectacularly beautiful. The walls glow with that intense blue color, light filtered through meters of ice. The ceiling drips continuously, and streams of meltwater flow across the floor. Everything is curved and smooth, sculpted by water, and the sense of being inside a living glacier, feeling it move and melt around you, is unforgettable. But these caves can collapse without warning, so exploring them requires expertise and caution. Ice climbing is a sport that depends on frozen waterfalls and ice formations. Climbers use special tools, ice axes and crampons, to ascend vertical or overhanging ice. The technique involves swinging the axe to embed its pick in the ice, kicking to set the crampon points, then moving up to repeat the process. Good ice is solid and reliable, absorbing the impacts without fracturing. Bad ice is brittle or hollow, shattering when struck or collapsing under weight. Climbers learn to read ice quality by its color, its sound when struck, the way it fractures, making split-second judgments about what's safe and what's not. The formation of icicles is something most people have observed but might not have thought about deeply. An icicle grows when water runs down from a warmer surface onto a colder one. At the tip, the water is coldest and freezes first, creating a point. More water runs down the outside of this forming icicle, and as it reaches the tip, it too freezes, adding another layer. The icicle grows in ridges because the freezing doesn't happen uniformly. It proceeds in pulses as water flows and temperature fluctuates. The result is that characteristic rippled texture. Icicles can grow to impressive lengths if water keeps flowing and temperatures stay below freezing, sometimes extending several meters from roof edges. Wind can sculpt icicles into curved shapes as it blows droplets to one side before they freeze. Multiple icicles can merge if they grow close together, and when sunlight hits icicles, they can act as prisms, splitting light into spectrums, decorating shaded walls with faint rainbows. There's something satisfying about the orderly row of icicles along a roof edge, their parallel forms, their regular spacing determined by wherever water happens to drip. Freezing rain is one of winter's more hazardous phenomena, distinct from both snow and sleet. It occurs when rain falls through a layer of freezing air near the ground and becomes supercooled, but stays liquid because there's nothing to trigger freezing. When these droplets hit any surface, the ground, a tree, a power line, they instantly freeze, coating everything in clear ice. Unlike snow, which you can brush off, ice from freezing rain bonds tightly to whatever it touches. It can accumulate quickly, weighing down tree branches until they snap, coating power lines until they break, turning roads into skating rinks. A severe ice storm can shut down entire regions, leaving millions without power, causing damage that takes weeks to repair. But if you can observe an ice storm safely from inside, there's a strange beauty to it. The world encased in glass, every surface shining, every branch outlined in crystal. When sun comes out after the storm, the sparkle is almost blinding, light reflecting and refracting from millions of ice-coated surfaces. It's beautiful and destructive at once. A reminder that nature doesn't care about our categories. It just does what physics dictates. Sleet is different. It's rain that freezes into ice pellets before hitting the ground. These pellets bounce when they land, making a distinctive sound, and they accumulate like hail rather than coating surfaces. Sleet is less dangerous than freezing rain because it doesn't create that slick coating, but it's still hazardous, reducing visibility and making surfaces slippery when compacted. Graupel, sometimes called soft hail or snow pellets, forms when supercooled water droplets freeze onto snowflakes, coating them in a layer of rime ice. The result is a small, round, opaque pellet that's softer than sleet and bounces less. Graupel falls from convective clouds, often in brief, intense showers, and it makes a distinctive drumming sound when it hits surfaces. It's common in spring when the atmosphere is unstable enough for convection, but cold enough for ice. All these different forms of frozen precipitation reflect the complexity of the atmosphere,
how the same water molecules can take so many forms depending on the exact temperature and humidity at each level. Forecasting which type will fall where is challenging, because small changes in temperature profiles can shift an area from snow to sleet to freezing rain. Snow rollers, those natural snow cylinders I mentioned earlier, are rare enough that many people who live with snow have never seen one. They require sticky snow, a good slope, strong wind, and usually a crust or icy surface for the snow to roll on. When all these factors align, chunks of snow break loose and the wind rolls them downhill, growing as they collect more snow. The center often stays loose or even hollow because it was the warmest part and doesn't bond as strongly. Finding a hillside covered with snow rollers is like discovering natural art. Dozens of these cylindrical sculptures scattered across the landscape, all created by nothing but wind and snow. Another rare phenomenon is snow donuts or snow bales, essentially the same thing as snow rollers but with a more pronounced hollow center. They look exactly like someone carefully rolled up snow into a jelly roll shape, except no one touched them. They formed entirely through natural processes. The hollow center forms when the innermost snow is too loose or too warm to bond properly, so it falls out as the roll continues to grow. Snowdrifts themselves are studies in fluid dynamics, even though snow is solid. Wind treats loose snow almost like a fluid, picking it up, carrying it, depositing it in patterns governed by the same physics that shape sand dunes. The lee side of a drift, downwind from the crust, is typically steeper than the windward side, creating an asymmetric shape that tells you which direction the wind was blowing. In a blizzard, drifts can form in minutes, burying cars, blocking doors, creating barriers where none existed an hour ago. The term whiteout describes conditions where falling or blowing snow becomes so thick that you can't see anything, not the ground, not the horizon, not the sky. In a true whiteout, you lose all sense of direction and distance. People have gotten lost meters from shelter because they couldn't see it. Flying in whiteout conditions is nearly impossible because pilots can't judge altitude or distance. Even walking becomes disorienting because you can't tell if the ground is level or sloped, near or far. It's one of the most dangerous aspects of winter weather.
But there's also something called a ground blizzard, where strong wind picks up snow that's already on the ground and blows it horizontally. The sky might be clear overhead, but at ground level, visibility drops to near zero. This can happen days after a storm, whenever wind picks up enough to move loose snow. Ground blizzards can close highways and trap travelers just as effectively as a snowstorm, but with blue sky visible above the blowing snow. The sounds of winter, beyond what I've already described, create their own acoustic landscape. The creak of tree branches laden with snow, sometimes snapping with a crack like a gunshot when the weight becomes too much. The whoosh of snow sliding off a roof all at once. The scrape of a shovel on pavement. The crunch of footsteps in various types of snow, each with its own pitch and rhythm. The silence of a snow-covered forest, where sound is absorbed before it can carry. And the wind, which in winter seems to have a sharper voice, howling through bare branches, whistling around corners, carrying the sting of snow with it. Animals have evolved remarkable adaptations to deal with snow. Ptarmigan grow feathered feet that work like snowshoes. Snowshoe hares not only grow wider feet, but also change color, brown in summer, white in winter, blending with snow to hide from predators. Ermines and weasels also turn white, giving them camouflage as they hunt. Some species grow thicker, longer fur that traps more air for insulation. Others increase their metabolic rate to generate more heat. And many alter their behavior, becoming less active, sheltering more, conserving energy when food is scarce and cold is intense. Migration is itself an adaptation to avoid winter, trading the energy cost of traveling hundreds or thousands of miles for the benefit of reaching places where resources remain available. Birds are the most visible migrants, but insects, fish, even some mammals migrate to escape winter conditions. Those that stay must have strategies for survival, whether it's hibernation, food storage, or the ability to find food even under snow. The relationship between snow and human culture extends into language, art, literature, and mythology. Inuit languages famously have multiple words for different types of snow, though the exact number is debated and often exaggerated. But the principle is real, that people who live with snow develop precise vocabulary for it. Similarly, skiers have a rich terminology for snow conditions because the distinctions matter for their activity.
In art, snow has been depicted for centuries, from Japanese woodblock prints showing snowy landscapes to European paintings of winter scenes. Artists struggle to capture snow's qualities, its whiteness that's not quite white, its ability to obscure and reveal, the way it changes light. Photographers find snow both challenging and rewarding, offering high-contrast scenes and unusual lighting, but requiring careful exposure to not just wash everything out. Literature uses snow as metaphor and setting, representing purity, death, isolation, transformation. Snow can be a gentle blanket or a killing force. It can bring communities together or strand people alone. Stories set in winter often have a different tone, quieter, more introspective, or sometimes more desperate. The symbolism is rich and varied across cultures. In mythology, snow and ice appear in creation stories, in tales of giants and monsters, in explanations for winter itself. The Norse had Skadi, goddess of winter and skiing. The Japanese have Yuki-onna, the snow woman. Many cultures personified winter as a being, sometimes benevolent, sometimes dangerous, reflecting the dual nature of snow as both life-giving water source and potential threat. Modern technology has changed how humans interact with snow, but hasn't eliminated the challenge. We have snowplows and salt trucks, heated buildings and insulated clothing, but we're still vulnerable to severe winter weather. Major cities can be paralyzed by heavy snow. Power grids can fail under ice accumulation. Transportation can grind to a halt. And individuals can still get into deadly trouble if they're caught unprepared in winter conditions. Snow removal itself is a massive industry in places with regular winter weather. Cities deploy fleets of plows, use thousands of tons of salt, employ sophisticated routing algorithms to clear streets efficiently. The cost is significant, running into millions of dollars per season for large cities. And there are environmental concerns. Salt runoff affecting waterways and groundwater, snow piles contaminated with road debris needing disposal, the carbon emissions from all that equipment running. Some places are experimenting with alternatives, using beet juice or cheese brine as de-icing agents, heated pavement in high traffic areas, better forecasting to pre-treat roads before snow arrives. The goal is to maintain safety while reducing environmental impact and cost. But so far, no solution works as broadly and cheaply as traditional methods. For winter sports, snow is the essential ingredient, and the industry depends on it. Ski resorts monitor snowfall obsessively, supplement with snowmaking when natural snow is insufficient, groom runs to optimize snow conditions. The economics are significant. Winter tourism generates billions of dollars, supports communities, provides employment, but shorter winters and less reliable snowfall threaten this industry, forcing adaptation, moving to higher elevations, investing in more snowmaking capacity, diversifying into summer activities. The personal experience of living with snow varies enormously. Some people love it, the beauty, the recreation opportunities, the way it marks seasons clearly. Others tolerate it, accepting it as part of where they live, dealing with the inconveniences. And some hate it, finding the cold, the shoveling, the hazardous driving to be too much hassle. These attitudes often reflect childhood experiences, how people first encountered snow, whether it was fun or frightening or just normal. For children, snow often means joy, sledding and snowmen, snow days off school, hot chocolate afterwards. There's a freedom in snow play, throwing snowballs, making snow angels, building forts. It's creative and physical and social all at once. Those childhood experiences create associations that last a lifetime, making snow a source of nostalgia for many adults, even if they find the reality less charming than their memories. The physicality of dealing with snow, shoveling particularly, is something that surprises people who haven't experienced it. Fresh, fluffy snow might seem light, but a typical driveway can contain several tons of snow after a moderate storm. Lifting and throwing that snow is real work, enough to cause heart attacks in those who overdo it. Wet, heavy snow is even worse, dense and exhausting to move. People who shovel regularly develop techniques, pushing rather than lifting when possible, taking breaks, working systematically. Snowblowers and plows make the job easier, but are expensive and require maintenance. In some neighborhoods, informal hierarchies form around who has equipment and who doesn't, with generosity or its lack becoming a social currency. These small interactions, helping a neighbor clear their driveway or choosing not to, are part of how communities function in winter. The quiet after a fresh snowfall is something that strikes many people, especially those who don't experience it regularly. Sound is absorbed, traffic is reduced, people stay inside, and the world becomes unusually hushed. Walking outside in this quiet, especially at night, can feel almost sacred, like being in a cathedral. Everything's soft and still and waiting. Your footsteps seem too loud, your breath visible in the cold air, and there's a sense that you're the only person awake in the world.
Night snow has its own character. The way street lights or moonlight illuminates falling flakes, each one visible for a moment before it's swallowed by darkness. The light catches the flakes in mid-air, creating a sense of motion and stillness at once, the flakes frozen in the beam even as they fall. And looking up into falling snow at night can be mesmerizing, the flakes appearing from the darkness above, streaming down past your face, creating an illusion that you're moving upward even as you stand still. Winter stars seen through cold, clear air seem brighter and sharper than at other times of year. The lack of humidity and the stability of cold air reduce atmospheric distortion, making stars appear as distinct points rather than twinkling smears. Combined with snow on the ground reflecting starlight back upward, winter nights can have a luminous quality, bright enough to navigate without a flashlight if there's even a bit of moon. The aurora borealis, the northern lights, are most often photographed in winter, not because they're more common then, but because the long nights provide more opportunity to see them. And viewing auroras over a snowy landscape adds another dimension, the ethereal lights reflecting off the snow, creating a world that seems to exist outside normal reality. Green curtains rippling across the sky, sometimes red or purple, moving in ways that don't match anything else in nature. And below them, the frozen earth, silent and white. Frost on windows creates temporary art, intricate patterns of ice crystals that grow overnight and disappear when the house warms in the morning. Each window might show different patterns depending on its temperature and the humidity inside. Before modern insulation and double-pane windows, frost patterns were common, and people would wake to find their bedroom windows covered in ferns and spirals of ice. Now it's rarer, but when it happens, it's worth pausing to look closely at the delicate structures, knowing they'll be gone in an hour. The concept of hygge from Danish culture is partly about creating coziness and comfort during long, dark winters. Candles, warm drinks, comfortable spaces, time with family. These are ways of making winter not just bearable, but actually pleasant. It's a mindset that acknowledges winter's harshness, but focuses on the opportunities it creates for different kinds of enjoyment. Many cultures have midwinter festivals, celebrations that break up the long stretch between autumn harvest and spring planting. These festivals often involve light, fire, feasting, an assertion of life and community in the darkest part of the year. Christmas, Hanukkah, Diwali, winter solstice celebrations, they vary in detail but share this theme of bringing light and warmth into cold and darkness. The winter solstice itself, the shortest day of the year, has been marked by humans for thousands of years. Ancient monuments like Stonehenge and Newgrange are aligned to solstice sunrises or sunsets, showing how important this turning point was to people who depended directly on seasons for survival. The solstice means the days will start getting longer again, that spring, however distant, is now approaching rather than receding. Snow in cities behaves differently than in natural landscapes. It accumulates on roofs and streets, melts from the heat of buildings and traffic, gets pushed into piles that become icy mountains lasting weeks. Urban snow quickly becomes dirty, absorbing soot and grime, turning gray or brown. It creates logistical challenges: where to put it all, how to keep roads clear without blocking sidewalks, how to maintain bus routes and garbage collection. But city snow also has its own charm. The way it softens the hard edges of buildings and pavement, how it brings a sense of pause to the usual rush, the temporary beauty before traffic turns it to slush. Children in cities often have fewer places to play in snow, but they're resourceful, sledding down parking garage ramps, building snowmen in tiny yards, having snowball fights on sidewalks. The smell of snow is subtle, more the smell of clean, cold air than snow itself. But people who live with snow often say they can smell when it's coming, a certain dampness and coldness in the air before flakes begin to fall.
Whether this is a real scent or a combination of other sensory cues isn't entirely clear, but the phenomenon is widely reported. Snow and rain together, that transition zone where precipitation can't decide what to be, creates some of the messiest conditions. Everything becomes wet and sloppy. Snow that won't pack, slush that soaks through boots, a chill that seems to penetrate deeper than dry cold. It's the least appealing form of winter weather, lacking both the beauty of fresh snow and the mildness of rain. The freeze-thaw cycle that happens in spring or in places with variable winter temperatures creates its own set of issues. Water melts during the day, seeps into cracks, then freezes at night and expands, making the cracks bigger. This process, repeated over and over, destroys pavement, creates potholes, damages foundations. It's one reason why winter is hard on infrastructure in ways that pure cold or pure warmth wouldn't be. The end of winter, when snow finally melts for good, is bittersweet for some. There's relief at warmth returning, at easier travel, at color coming back to the world. But there's also loss, the unique beauty of winter disappearing, the sports and activities ending, the landscape losing that simplifying blanket. Spring mud season lacks the charm of either winter or summer, everything brown and soggy and exposed. But as meltwater flows and ground thaws, life resurges. Plants that have been dormant for months begin to grow. Migrating birds return. Hibernating animals emerge. The moisture from melted snow soaks into the ground, replenishing aquifers, filling streams, supporting the green-up that turns hillsides from brown to brilliant green in a matter of weeks. And already in the atmosphere, processes are continuing that will eventually bring snow again. Water evaporates from oceans and lakes, rises into the sky, waits for the next cold season. The cycle continues, has continued for as long as Earth has had ice ages and seasons, will continue long after we're gone. Snow is temporary in any particular place, but as a phenomenon, it's eternal, one of the basic modes of water on this planet. Looking at snow this way, seeing it not just as cold white stuff, but as a complex, beautiful, important part of Earth's systems, changes how you experience it. Each snowflake becomes more interesting when you know its journey. Each snowy landscape becomes richer when you understand the processes creating it. And winter itself becomes not just something to endure, but something to appreciate. A season with its own gifts, its own lessons about impermanence, beauty, and the endless creativity of nature. So tonight, as you drift towards sleep, maybe you can imagine snowflakes forming high above, each one growing its unique structure, each one beginning its long, tumbling journey downward. Maybe you can picture vast snowfields reflecting starlight, mountains honed and winter in their heights, forests hushed under their white blanket. Maybe you can hear that soft, continuous whisper of falling snow, feel that stillness that settles over snowy landscapes, sense that particular quality of winter peace. The world covered in snow is a different world, simplified, softened, slowed. And there's something restful about that, something that invites the kind of deep quiet that naturally leads into sleep. So let yourself sink into that quiet now. Let the gentle images of snow and ice and winter calm drift through your mind, each thought soft and light as a snowflake, each breath carrying you deeper into rest. If these quiet science stories help you relax and sleep, I'd love it if you'd watch another one. There's more peaceful explorations waiting for you, more gentle journeys through the hidden wonders of the world. But for now, just rest. Let winter's peace settle over you like falling snow, covering everything, softening everything, until there's nothing left but quiet darkness and the gentle pull of sleep. Good night.